Hey guys, how's it going? So yesterday I just finished my second midterm for complex analysis. And I'm going to review with you my answers and how I felt during the entire process of taking this 50-minute test. So yeah, there were 4 questions. It was out of 20. Um, it didn't feel so bad. It felt much easier than the assignments, which makes me think maybe I should do a video on some of the difficult assignment problems. The difference is like night and day. I'm not even gonna lie. All right, so here are the 4 questions. Question 1, show that z0 equals 0 is a pole of the function f of z is equal to 1 over z to the power of 4 times z plus 2 and determine its order. B is use residues to find 1 over z cubed multiplied by z plus 4 c dz. Evaluate this integral basically, where c is the circle radius 2 centered at the origin. So part A, z naught equals 0 is an order of 4. I don't really know how to write a proof of this. So the way I said it was like f is a rational function, and rational functions are analytic everywhere in C except where the denominator is 0. At 0, f is obvious, the denominator there is obviously 0. Z naught is a place the denominator is 0. So it is a pole. Now it's not an essential singularity or a removable singularity. It's an isolated singularity because it's only at the points where the denominator is 0, because like everywhere else in the neighborhood of 0, the function is differentiable. So yeah, everywhere else in z equals 0's neighborhood is analytic. So the order is 4, and the way you do it is like, say f of z is equal to phi over z divided by z minus z naught to the power of m. And then, yeah, z naught is 0, so it's z minus 0. Phi over z is 1 over z plus 2, and phi over z cannot be 0, but it's very clearly, phi of 0 is very clearly not 0. So hence, it's a pole of order 4. 1b, f of z would be 1 over z cubed times z plus 4. This c has a circle of radius 2 and the center at the origin. I drew that. It's asking, the question's asking about the, this. So f of z is a rational function, and rational functions are analytic everywhere except at the denominator where the values are 0. And here it's 0 and -4, where the denominator is 0 and thus not differentiable there. We don't care about z equals -4 because z equals -4 is not within this C. So we only care about the pole z equals 0. Now, so phi of z is equal to 1 over z plus 4, and z equals 0 is a pole, and it has an order m equals 3. Calculating the residue of this, so m equals 3. So you have to find 3 minus 1 is 2. So you have to find the second derivative of phi of z and divide it by 3 minus 1 factorial, which is 2. So phi of z is 1 over z plus 4. Differentiate it twice, and you get phi prime prime of z is 2 times z plus 4 to the power of -3. So b, which is the residue, is phi prime prime of 0 over 2 factorial. So that's this. Do the calculation, you get a value of 1 over 64. C f of z dz is 2 pi I times the residue. So that gives you pi over 32 I. I'm like 90% confident I'll get full marks for question 1. But then again, my teacher is very picky, so I don't know. Question 2, show that f of z equals 1 minus cos z over z squared, and then here z is not equal to 0, and that's a half at z equals 0. Show that this is entire. You may take the series for cosine as known, and the fact that g of z equals cos z is entire. So they're telling you that cosine z is entire. So don't go plugging in cos of x plus iy and then trying to use the Cauchy-Riemann equations. They're just telling you that g of z equals cos z is entire. And part B, find the Laurent expansion about z naught equals 0 of f of z equals 1 over 1 plus z valid in the region this, and explain why it is valid there. Okay, so let's do them separately. Part A, first of all. The very first thing I'm going to do is I'm going to establish that f of z is continuous along the entire complex domain. And why do I do that? Well, that's because, well, remember that in calculus 1, that if a function is continuous, it might or might not be differentiable. But if it's not continuous, then it's definitely not differentiable. So if f is continuous, it's a necessary, but it's not a sufficient condition. But we have to establish this first. So let's see if it's continuous at f of 0. It's continuous elsewhere in the complex domain. So let's just focus on 0. So first, 1 over cos z over z squared. This gives you a value of 0 over 0. We're going to use L'Hopital's rule to evaluate the limit at z equals 0 of this. So let's do that. That's 0 over 0. Okay, so 1 minus cos z, the derivative is sine z. This is 2z. That's 0 over 0. Still apply L'Hopital's rule again. The derivative of this is cos z. The derivative of this is 2. So you get 1 over 2. And hence f of z is continuous at z equals 0. It's a necessary but not a sufficient condition. So continuity is established. Next, cos of z is equal to this series. I'm going to do a video in the very near future, the very, very, very near future, about the Maclaurin series in Calculus 2. So hang on to your hats there, and I'll get to it. So cos z is this Maclaurin series. And when you expand this out, you get 1 minus z squared over 2 factorial plus z4 over 4 factorial, so on and so forth. And this is the radius of convergence. Now, when you expand this, so 1 minus cos z over z squared gives you 1 minus all of the value of this. So I've just plugged it in over z squared. When you do that, okay, so 1 minus 1 is nothing. Okay, then minus minus becomes plus z squared over 2 factorial. So then when you do this calculation, you get 1 over 2 factorial plus z squared over 4 factorial minus z to the power of 4 over 6 factorial. And you just get left with a bunch of polynomial terms, basically. And this goes to establish that z equals 0 is a removable singularity. Because 1 minus cos z over z squared has now been reduced to a sum of polynomials. And polynomials are known to be entire. So based on this, and that f is continuous throughout the complex plane, f of z is entire. Yeah, so a removable singularity we learned in class is basically a singularity that appears to be, it initially at first glance appears that f is not continuous or differentiable at that point. But when you work it out, you realize that f is analytic at that point, continuous and or analytic at that point. Yeah. So part B. f of z is equal to 1 over 1 plus z. That's the way they did it. I just said it's 1 over z plus 1. It's the same thing. I'm going to divide both the numerator and denominator by z. So you get this. Okay, so then that's 1 over z. And then you get z, this series, negative 1 to the power of n, 1 over z to the power of n. And then you get negative 1 to the power of n as z to the power of n plus 1 starting at n equals 0. And I, what did I do? Yeah, and then I moved it at n equals 1 because this is a Laurent expansion. All the exponents are negative for z, so you have to make it at n equals 1. And this is actually valid at 1 less than absolute value of z less than infinity because, well, I originally had it like this. And I'm going to make a side note. There, for the Maclaurin series, 1 over 1 minus q is equal to n equals 0 to infinity, q to the power of n, absolute q. This is the radius of a convergence originally when you have something like this. So do some substitution. And here, so this equals 1 over z times 1 over 1 plus 1 over z. So substitute 1, negative 1, because that's 1 minus negative 1 over z. So negative 1 over z is q, so you can substitute. The absolute value of negative 1 over z is the same thing as the absolute value of 1 over z less than 1. That means absolute value of z is less than infinity, but absolute value of z less than 1 already has a different series representation, so the validity is established at 1 less than absolute value of z less than infinity. My reasoning was my wording is a little watery. I'm pretty confident about this. I don't know. I'm thinking a 3.5 or a 4. I really hope. Hopefully a 5. Please, professor, I'm just trying to graduate. Give me the marks. Okay, part 3. A. Show in 2 different ways that C, this integral around a contour is equal to 2 pi I, where C is basically the unit circle, no, not the unit circle, is a circle of radius 1 centered at Z naught. And B, prove that F is an entire function, if F is an entire function such that lim z goes to infinity, f of z over z absolute is 0, then f is constant. I'm very confident about A. I was actually able to find 2 ways to show this is true. The first way is I used Cauchy's integral formula. It's actually Cauchy's. No, I'm just joking. F of z naught is equal to 1 over 2 pi I c f of z naught over z minus z naught. This is a true formula. I've memorized this at heart. It's near and dear to my heart. Then substitution, algebraic manipulation, 2 pi I f of z naught is equal to c integral f of z naught over z minus z naught dz. Well, based on the looks of here, f of z naught is very clearly equal to 1. So knowing that 2 pi I is this c integral dz over z minus z naught. That's the first way you do it. The second way is another formula. Okay, so I'm going to parameterize this z in terms of t. Z is equal to z naught. The unit circle is expressed as e to the power of it. So it's z is z naught plus e to the power of it. And when evaluating a contour, c, this is the general formula, c f of z dz, it's equal to, from t1 to t2, f of z of t times z prime of t dt. And that's equal to, so here, if the unit circle goes from 0 to 2 pi, so it's 0 to 2 pi. I skipped a few steps here. So let me explain now. Z prime of t is just I e to the power of it. And f of z of t is 1 over z minus z naught. Okay, so z is this. Z minus z naught is z naught plus e to the power of it minus z naught, but then the z naughts cancel out, so you're left with e to the power of it dt. This cancels out, so you're left with 2 pi I when you evaluate this integral. I'm going to make a bit of a note here, guys. I'm kind of certain that I'm going to get docked marks for not including all the details. But let me tell you this. When you're in a timed exam situation and you don't have time to write everything, skip a few details. It's better to go too fast on an exam than too slow. Because if you go too fast, at least you'll know you answered all the questions and maxed out your potential. If you go too slow, you could have had the potential to answer questions that you weren't able to answer. So if I get docked for not including all the necessary calculations here, so be it. I'm pretty confident I'll get at least a 4. No, sorry, at least a 2 out of 2.5 for part A. Part B, show that f of z has to be constant. Let f equals f of z and let g equals g of z. I'm very not confident about my answer, but I thought it was kind of logical. I just used calculus 1 knowledge to do this, honestly. I basically said that g of z has a degree of 1 as a polynomial. So if this limit goes to 0, then f has to have a degree of less than 1 for this limit to be 0. So it has to have a value of less than 1, but it could be 0.25, it could be 0, it could be -1. It has to be 0 because if it's any other value, then it's not continuous along the entire complex plane, thus not entire. So I said f has to have a degree of 0, so f is constant and it's a polynomial and it's entire. I'm not very confident about this answer. I hope I get some marks for this. Question 4. If f is analytic and in a bounded domain D except for poles, explain why the set of poles has no accumulation points. B, show that 0 is an essential singular point of f of z equals e to the power of 1 over c. And in C, in question 1b, you evaluated this integral. Now find the same integral along a square whose sides lie along the lines x equals plus or minus 3, y equals plus or minus 3. Explain your answer. Okay, so for part A, I just BS'd my way through it. I just did a visual representation. F is analytic in a bounded domain D except for poles. I said poles are not part of the domain. So like the neighborhood, the neighborhood is not part of like the domain, like, so it's not an accumulation point. I don't really know part A. I don't think I'm going to get points for A. For B, I'm pretty confident I'm going to get this one. So I just did substitution. E to the power of z has the Maclaurin series from 0 to infinity of z to the power of n over n factorial. So substitute z with 1 over z. So e to the power of 1 over z is n over equals 0 to infinity, 1 over z to the power of n factorial. And that's equal to 1 plus 1 over 2 factorial z squared plus 1 over 3 factorial z cubed plus 1 over 4 factorial z to the power of 4, so on and so forth for the rest of the series. Now observe, for the rest of the series, which is infinite, z equals 0, the order of z equals 0 increases its order infinitely forever. So z equals 0 is a pole of infinite order by the Maclaurin series, so it's an essential singular point. It's not like a removable pole where it has a finite order. Like for example, in question 1, in question 1b, z equals 0 has an order of 2. No, sorry, z equals 0 has an order of 3, which is a finite number. So that is a isolated singularity. This is an essential singularity. Yeah, since it has an order of infinity. Part C. We evaluated this integral in question 1b. It's still pi I over 32. Let me explain why. You don't have to evaluate this integral again. You can do a shortcut. The original question in 1b had the circle of radius 2. Now you're evaluating it around a square of bounded by x equals plus or minus 3 and y equals plus or minus 3. Notice that x equals -4, no, sorry, z equals -4 is not contained within C, but the pole x, the pole z equals 0 is. So just like 1b, there is only one pole at c equals 0 in C. Since the circle absolute value z equals 2 in C is contained in C, hence this is still pi I over 32. So there's a theorem in that I learned. It's like if you have a pole contained in like this figure, and then this pole is also contained in the bigger figure, the value of the integral for both figures are going to be the same, assuming they're rotated counterclockwise. So because the circle of radius 2 is also within C, and since this value was pi over 32, this value will also be pi I over 32. So yeah, that's the test for today. Honestly, up until this point in my university career, every second midterm has been atrocious. The highest I got was 22 out of 30 on a second midterm. I have a feeling I'll break the tie. I'm hoping for a 16 out of 20, but life can be so unpredictable at times. I'm not going to set my expectations too high because the last thing I want is me hoping to get a 90 and then ending up getting a 40. So yeah. I'd love to stay in chat for now, but I have to jump. I'll see you guys on the other side of the bridge. Catch you next time.